So in contrast to the real numbers, we have the complex numbers. And the complex numbers are typically denoted with a boldface C. And they are the set of thingies that look like A plus B times I, where A and B are both elements of the real numbers. So A and B are real numbers. And then I squared is equal to minus 1. Or more often we just say I is equal to the square root of negative 1. And I'll talk more later about what I mean with this notation here, where we've got the curly braces and the such that colon and stuff like that. But for now, let's just proceed as if this makes sense, and take it from there. So geometrically, this is just by comparison with what I wrote in the previous clip. Geometrically, complex numbers are points on a plane. So we have two axes, and we can go now in infinitely many directions from the origin, because we can go left, right, up, and down, but also at any angle, right? So in terms of the geometric structure of the set, it looks just like the plane R2. The only thing that's different is that there's a multiplication defined. There's a way to multiply two numbers. So let's look at it algebraically. So algebraically, again, it's going to be now exactly like the real numbers, but now it's going to be closed under taking roots. So what do we have? So for example, what do I mean by that? Well, let's take a look. So if I look at the square root of negative 1, positive or negative square root, these guys are elements of, or exist in the complex numbers, but not in the real numbers. So if you notice, we have that this number here, I, is a root of the polynomial x squared plus 1, right? So x squared plus 1 equals 0 cannot be solved in R. In other words, if we require the solution to be a number from R, you can't solve it. But in the complex numbers, you can solve it. Okay. What else? Well, so that's what I mean by closed under roots, taking roots of polynomials that have coefficients from the set. So here's another example. Say we take like 3.7 x squared minus pi times x, pi is a real number, right? Plus 2 equals 0. Okay, can this be solved? Can we find the roots, the x's that satisfy this equation? Well, it can be solved in C, so those roots exist as complex numbers. And there will be two solutions. And that's because we've got, whoa, that was a big pen. Well, okay, good enough. There. That's because we've got this number 2 right here. So I know there's going to be two solutions. Can it be solved in the real numbers? Actually, it turns out no. That's not an easy thing to see. That's something that you need a computer probably to work out. And in fact, in order for it to be solvable in R, by poking around with Mathematica, it looks like this number here, 2, needs to be bigger than something like 7.83 in order for this thing to have roots in the real numbers. Does that matter? No, it's completely irrelevant. I just wanted to show you that for a given polynomial, determining whether or not the roots are complex or real is not at all easy. And there's a whole lot of work that goes into that kind of stuff. Okay, so back to the main point. The complex numbers form a system that we say is algebraically complete. And that just means that roots of polynomials are in the set. So if we take something like an times x to the power n plus an minus 1 x to the power n minus 1, etc. So this is the general form for what a polynomial looks like. Plus some constant a0. And if all of these coefficients, these AIs, so that's these coefficients that I've got in front of the x's all the way along here, where all these AIs are real numbers. And so if you haven't seen this element symbol before, this just means AI is a real. Or a complex. Then the equation px equals 0 has n solutions in C. That's the meaning of algebraically complex. If you have a polynomial of order n, then there's n solutions. And that's with multiplicity. So it could occur that you have, like a double root or something like that. That can happen, right? So this statement is saying the same thing as saying that I can rewrite my polynomial. So I can take it from this form that it's in right here, and I can rewrite it as in a factored form. Right here. And so if I write it in this form right here, then you can see that each of these numbers in the parentheses, those are roots. If I set C equal to C2, for example, then what happens? Well, then this term right here is going to be equal to 0, and then the whole thing would equal 0. So I can see from that P of C2 is equal to 0. So this is just a fancy way of saying I can factor it into n terms, and that's what you can do in C, in the complex numbers. And the key point here is that maybe you can't do this with real roots. And so your standard example for that is, again, x squared plus 1 equals 0. Well, this one can be rewritten as x minus I, x plus I. So it factors into these two, or it splits into these two linear factors. And you can see from this that the roots of this polynomial are I and minus I. And those just happen not to be real numbers.